Bon, je suis très heureux d'être là aujourd'hui pour ce congrès en honneur de Denis Tallet. Bon, tout le monde connaît Denis Tallet, mais pour moi, c'était une chose très personnelle parce que disons que Denis est le premier probabiliste français que j'ai connu. Ça se passait en 90, c'était dans un congrès, ça venait de s'ouvrir la Roumanie, et donc j'ai pu sortir et c'était un congrès à Leipzig, je crois, en Allemagne de l'Est. C'était pas le même congrès que celui que Bernard Lapère a montré, c'était un autre, je crois. Et bon, je suis arrivé là, il y avait un groupe de Français qui étaient en cercle, comme ça, ils parlaient seulement entre eux. Et bien sûr que moi, je parlais très bien français à ce moment-là, donc je suis rentré immédiatement dans le groupe, et là, j'ai trouvé Denis. Et Denis m'a immédiatement parlé du schéma d'Euler, le travail qu'il était en train de se faire avec Tubaro, un travail qui est resté fondateur dans ce domaine. Et moi, j'étais préoccupé à ce moment-là du calcul de Maillard-20, et immédiatement, Denis a vu la possibilité d'appliquer les techniques du calcul de Maillard-20 pour obtenir des régularités de la convergence en variation totale dans les erreurs dans le schéma d'Euler, et puis de la densité dans le schéma d'Euler. J'étais très impressionné par le fait suivant que, donc Denis, à ce moment-là, il ne connaissait pas le calcul de Maillard-20. Après coup, il est devenu un spécialiste, mais à ce moment-là, il n'en connaissait pas. Mais quand même, il avait une idée globale très précise et très pertinente de ce qu'on pourrait attendre d'obtenir avec ça. On peut employer le mot effet régularisateur ou quelque chose comme ça, mais il le manipulait très bien, dans le sens où il trouvait exactement ce qu'il peut faire, même sur des aspects techniques, s'il y a beaucoup de bruit, s'il y a moins de bruit, qu'est-ce qu'on va faire dans ce cas. Donc il y a eu pas mal de discussions à ce moment-là, et après coup, j'ai obtenu une bourse, et donc je suis arrivé en France, et donc j'ai eu l'occasion de travailler avec Denis, et c'était extraordinaire. Et donc, j'étais invité par Denis à Sofia, où on a collaboré, on a travaillé assez longtemps. Bon, à part ça, ce que je peux dire, c'est les exigences de Denis. Il voulait toujours faire les choses d'une manière excellente, jamais à un niveau plus bas. À un certain moment, moi, j'étais un peu fatigué, désespéré devant le niveau de technique, de l'effort technique qu'il fallait faire. Et j'ai dit, Denis, on va s'arrêter avec uniforme ellipticité. Et Denis, avec une voix très douce, m'a dit, mais non, on va faire quand même sous la condition de Remander. Et c'est ce qu'on a fait finalement, il avait raison, et c'est ce qu'il a fait. Voilà, donc ça c'est la partie heureuse. Il y a eu une partie un moment un peu plus tragique. C'était que, je me rappelle pas bien si on était ici, au CIRM, ou si on était à Sofia. Il y avait un congrès. Et puis, le soir avant, on venait de manger, on était à table, et on s'est rendu compte, Denis et moi, on s'est rendu compte que le schéma d'Euler ne vérifie pas les conditions de Remander. Et puis bon, on s'est regardé l'un l'autre et on a dit, en fait, je ne sais pas ce qu'on a dit, peut-être on n'a rien dit. Le lendemain, j'ai fait l'exposé. Et puis, Dieu merci, après, dans la semaine qui a suivi, on a fait un gros effort. Et bon, il y a eu des idées assez simples qui nous ont permis de remplir ce gap-là. Et les choses ont marché finalement. Mais le moment où j'ai parlé, je me rappelle que il y avait Smithman dans la salle et quelqu'un a demandé une chose à Smithman, j'entendais pas quoi, et moi je me suis dit, ils ont découvert les roses. Ils se sont rendus compte que ça marche pas, mais ils n'ont rien dit, je sais pas ce qu'ils ont découvert ou non, mais ils n'ont rien dit. Et donc bon, finalement c'est fait, et c'est sûr que c'est, disons, le travail auquel j'ai eu le plaisir de participer, qui a eu le plus d'impact de tout ce que j'ai fait. Voilà, donc je suis très content de cette collaboration et de l'amitié qui a suivi. Bon, maintenant je vais donner un talk sur la construction de solutions d'équations en employant le sewing argument. Ce n'est pas la première fois que je fais cet exposé, mais je ne pouvais pas faire autre chose parce que J'ai encore 5 minutes? Oui. Voilà. Je n'ai pas faire autre chose parce qu'en fait, le sewing lemma, c'est une technique pour tenir en main des schémas d'Euler. Or, si on est pour un congrès de Denis, les schémas d'Euler, c'est une chose très importante. Et donc, je vais parler d'un travail qu'on a fait il y a 2 ans en collaboration avec Aurélien Alfonsi du CERMIX, de l'École des ponts et chaussées. Voilà. Et donc, en premier temps, je vais expliquer les équations dont je vais m'occuper. Ce sont donc des équations de type Boltzmann ou McKean Vlasov. Donc ici, ce que je mets ici, c'est une équation analytique en forme faible. Donc la solution de cette équation, c'est une famille de mesures de probabilité. Ici, on les intègre contre des fonctions test, phi. Et on a la forme faible, weak form, the weak form of the equation. I will speak anyway English, maybe it's better, I don't know. My French is better than my English, but anyway. And so you have the equation, and you have here the blue things that the solution appears, the solution comes on in the coefficients, and this is a McKean Vlasov type effect. But the solution comes on also in the integration here, and this is related to the Boltzmann type contribution. And so the solution is just a family of probability measures which verifies this equation. This is analytical form of the equation. And then there is a probabilistic interpretation of this equation. And we have here the xst is equal to capital X, the initial value, plus integral from s to t of b of x. And here appears the law of the solution xsr. And then you have an integral of, with respect to a Poisson point measure of coefficient c, which depends on the solution x and on the law of the solution. This is a McKean Vlasov type contribution. And then the integration here with a measure, with a Poisson point measure, depends on the law of the solution. So the compensator, the intensity of the Poisson point measure, is given by the law of the solution dV, multiply some mu dz as a measure, ds du dr. U appears here. So the idea with this equation is that you have a particle xst, which is the principal part, and the main particle, and it evaluates in some frame where there are other particles which have the same law as x, and they interact. And here is the measure of the intensity of the measure of interaction. Okay, this appears as a probabilistic interpretation of the previous equation, and this was introduced by Tanaka, which proves that if you have x, the solution of this equation, then FSR dx, which is the law of x, solves the previous analytical equation. And so this was a first result of Tanaka, but afterwards Sylvie Melléard and Nicolas Fournier, they worked a lot and gave a lot of results related to this probabilistic point of view on this equation. So these are two ways of saying the same thing, say, the analytical weak equation and the probabilistic interpretation. And so now a first thing that I will do is to give a third way to formulate the same problem, so which is an alternative way to formulate the same problem. So I consider P1 to be the probability measures which have first moment, and W1 to be the Wasserstein distance on this probability space, on the space of probability measures. And then I denote by A the space of application theta from P1 to P1. And the distance that I consider on A is the distance, so theta and theta 1 are applications, okay? The distance to theta theta prime is the supremum of W1 of theta rho and theta prime rho, where rho is in a probability measure and is normalized with the first moment of rho. So we have, this is a framework in which I will work, and so we have two spaces here, P1, W1, and A, which is the application with this distance A, D star, and both these spaces are complete probability spaces, complete metric spaces, pardon. Okay. And so, okay, this is a framework. And now I will introduce the main object which appears in my talk, which is a one-step Euler scheme. So, what is this one-step Euler scheme? I take rho to be a probability measure in P1, so a probability measure which has a moment of order 1. And then I take a random variable x, which has a low rho. And these are given, and I construct the following process. YST of rho is equal to x plus bx rho t minus s plus here is an integral with respect to the Poisson point measure, in which I have the coefficient, in the coefficient C I put x, I put rho, which are fixed at the beginning, and here gamma is dependent on x, and the Poisson point measure here has intensity, which is given by rho. It's completely clear that this is an Euler scheme which is associated with this equation, okay? Because what I am doing is that I've frozen here XSR to be x, the initial point x. The low I put, instead of the low L, I put rho, which is the low of x. And this is what I'm doing everywhere. I replace with frozen things. Okay, so this is just the one-step Euler scheme. Okay, so I define the one-step Euler scheme, and then I define a transformation which goes from P1 to P1, which rho is transported in theta st of rho, which is the low of this thing. It's clear that this is already solved. I have to solve nothing. I just put something like this, and I define theta s rho to be the law of YST rho. And this is the main object in my talk. It's the one-step Euler scheme, which is defined in this way. And now I give the main result is the following theorem. We prove that there exists a unique theta st in A, so the unique transformation, unique family of transformation theta st in A, such that theta is a flow. So going from S to T is the same thing that going from S to R and from R to T, so it's a flow. And small theta is close to capital theta at the level of T minus S is St here, St, T minus S power 2. If it was T minus S power 1, it was like a derivative. It's power 2, this means the derivative goes to 0. So they are very close each another, okay? And so the theorem says that under some condition, of course, under some conditions of the coefficients B and C, there exists a unique flow theta st, which is a flow and which is close to the one-step Euler scheme. And this theta, I call this theta flow solution. What we prove that it exists, such a theta, and we prove also that this theta, this is a family of probability measures, and this family of probability measures solves the weak equations that I put on the first slide in the beginning. This is one point, and at the same time, it represents a stochastic representation of small theta. So I mean that I have behind the diffusion process which has low theta st like this. So this is the main result that we prove in this paper. Apart this, so what I mean is that here with this flow solution that I defined here, we have somehow a third way to. We have two ways to give solutions, weak equations and diffusion process, which gives the interpretation, the operator interpretation. And here we have a third way to define the solution, which is the notion of flow solution. This is somehow in between probabilistic and analytic in the sense that the small theta, so the solution is defined not by an infinitesimal operator, but by something which is similar. Small theta is close to capital theta, and capital theta itself is the one-step Euler scheme associated to this problem. So this is somehow intermediary between probabilistic and analytic, and something which is somehow as the capital theta, the one-step Euler scheme, replaces the infinitesimal operator. Okay. And so this point of view of this way to define solutions of equations is not new. It's inspired from a paper of Davy. Davy worked in the years 2004, 2006, something like this. He works on the rough path theory, which has, the rough path theory has nothing to do with what we are doing here. But there are some ideas which we borrow from these things done by there. For example, this way to define solutions in the sense of Davy, in some sense. This is one thing that I have to mention. Another thing is that we discussed up to now about one-step Euler scheme. You can do, you concatenate one-step Euler schemes, and you obtain a real Euler scheme. So if you fix S0 less S1 less Sn, a partition, you can construct using one-step Euler scheme, you construct a real Euler scheme. And what we prove also is that the distance between the flow solution and the Euler scheme is less than t minus s, s and t are given here, multiplied by the step of the partition. So we get not only the fact that the solution exists, but also a speed of convergence approximation in terms of the step of the partition. The truth is that not only we get this speed of convergence, but the small theta, the flow solution itself, is constructed as limit of Euler schemes. We prove that Euler schemes with step which goes to 0 form is a Cauchy sequence, and so they give the limit. We are in the spaces which are complete. The limit is this small theta. So this is somehow the construction is through Euler schemes. Okay, that we have an estimate of the error. We have also uniqueness. Generally, the problem of uniqueness for such equations may be a little bit difficult, but with flow solutions, this is immediately obtained, because if you have two flow solutions, they are all the time limit of Euler schemes that, of course, are the same Euler scheme, and so they are unique. And so this is an advantage of this method. And finally, a result which is sometimes in concrete situation a little bit difficult is about stability. So if you start from rho, or if you start from psi as initial values, theta st rho, theta st xi in W distance is less than t minus s W1 of rho and xi. And so you have also stability. Okay, so this is the result, and maybe some consequences related to him. Now I will say some words about the proof and about the main instrument, which is appears in the proof, and which is the so-called sewing lemma. Ah oui, c'est ici. The sewing lemma. So this sewing lemma appeared also in the framework of related to rough pass theory, and it was introduced in the same way and in the same time independent way by Gubinelli in 2004 and by Fayel and de la Pradelle in the same time. And they introduced this lemma, and which simplified greatly the approach to rough pass equations. And the sewing lemma is about things, random variables with values in RD. And here we have not random variables in RD, we are in the Wasserstein space. So it's a little bit different. But and also we are with this framework of flow solutions, or flows of probability measures. And I have to mention that in 2015, Ismaël Bayeul, who is, I think that now he's a professor in Brest, it was in Rennes at the time, he also have noticed that this point of view of flows is very good in the framework of sewing lemma. Okay, so these are people who worked before, and now I give the sewing lemma. It's like this: you have A of V, a family of transformations of a space V in a space V. In our case, the space V is P1, and you have theta st to be a family of transformations like this. In our case, it's a one-step Euler scheme. So we have P1, we have the one-step Euler schemes, and we construct the real Euler scheme associated to partitions. So these objects, we have them. And now I make the following two hypotheses. The first hypothesis is the hypothesis of Lipschitzianity. Theta p st composed to u, theta p st composed to u prime is less than the distance from u to u prime for every u and u prime in A. So there is a Lipschitzianity property as the stability with respect to the initial value. So this is one hypothesis. And the second hypothesis is one. I will call the so-called sewing properties that I recall here and I discuss a little bit more. If capital theta was a flow, so capital theta, if I go from S to R and from R to T, is the same thing as if I go from S to T. This is a flow property. But the one-step Euler schemes that I have constructed before do not have this property. So there is an error. And this, what I have here, is an error with respect to the flow property. And I suppose that error is small, less than t minus s power 1, so it's normal. So this is just nothing, is a good range, but 1 plus epsilon. And so epsilon goes, this makes that this quantity will go to 0, even normalized with t minus s, when t minus s goes to 0. And so, so I have a family of applications which are Lipschitz, and we have the sewing property. And then the sewing lemma says the following thing. Under these two hypotheses, there exists a unique flow theta st of transformations from V to V, in our case from P1 to P1, which is a flow, so the error is 0 here, it's a flow, and which is close to capital theta to level t minus s 1 plus epsilon. So this is the sewing lemma, and it's completely clear that is what we need in the previous theorem. Okay, so now I will discuss a little bit about the proof of the theorem. So if you have, I do not discuss about the proof of sewing lemma. So I suppose that the sewing lemma is it's okay, and I will see how I can use the flowing lemma in order to, je sais pas où, in order to solve my problem, attends, ça c'est... Non, ça c'est... In order to produce the flow solution. So the solving lemma is somehow in an abstract framework. I will want to put it at work in the framework of equations where capital theta is given by the one-step Euler scheme. This is what I try to explain in this moment. The main step in the proof is the following stability result. So I define YST of rho and x. So I fix rho and I fix x. X is a random variable, rho is a probability law. And I define something which is exactly the one-step Euler scheme, but I do not ask that x has low rho. I take general rho and general x, which are not specifically linked to each another. And so I have this one-step Euler scheme, and I define theta st of rho and x to be the law of this Euler scheme, one-step Euler scheme. And the stability result I speak is the following. I take rho and x, I take rho bar and x bar, and then the distance between W1 theta st of rho x and theta st of rho bar x bar, I will prove that is less than the expectation of x minus x bar plus W1 of rho bar multiplied by 1 plus T minus S. So I will prove this thing. And this thing immediately implies that if I go, here is a one-step Euler scheme. Now if I take a composed Euler scheme, a real Euler scheme, the distance between the Euler scheme in rho x and the Euler scheme in rho bar x bar is less than ax minus x bar plus W1 rho minus rho bar multiplied of the term from here is given exponential. I will prove that, so this is what I prove. And I tell some words about this proof. How I prove this. So in the moment that this is proved, afterwards the theorem will follow in a rather easy way. But for the moment, let us see how it is proved. I have two things, rho and rho bar, two probability measures. And these two probability measures comes on here. You have a Poisson random measure, which is with measure rho dV, and I have rho bar, so another Poisson random measure with rho bar dV. So if you want to compare this guy with the guy where rho is replaced by rho bar, you are in a bad situation because you are on different probability spaces, and you are not able to use some L1 or L2 calculus because you are not on the same probability space. So this is somehow the real difficulty, the small difficulty, the real difficulties that you have at hand. You are not on the same probability space, and then you cannot use a priori L1 things. And so what you have to do is to get on the same probability space. And this is done like this. You have rho and rho bar, you take an optimal coupling of rho and rho bar. And this is not all. Afterwards, this optimal coupling, you express it, you represent it by means of a transformation tau, function tau from 0, 1 to Rd time Rd. So you may find some tau from 0, 1 to Rd by Rd, which verifies this equality. So the integral from 0 to 1 of f of tau of w dw, it's equal to the integral on Rd time Rd of f x x prime with respect to the measure p rho bar of dx prime. So tau in some sense represents the measure p, but the measure p is on Rd time Rd, and here the tau is with respect to the Lebesgue measure. And so this is an important point to have this representation. And now we have it. We also couple the initial values x and x bar. We couple optimal coupling, and I express x prime x bar prime as marginals of this optimal coupling. And then I define exactly the same thing as above, the one-step Euler scheme. But now I take a Poisson point measure, which is an objective Poisson point measure, and which has intensity dW, which is the dW here. So, and I transport the contribution of rho in tau of W, which appears here. Okay, so I have this new representation as the law of this y prime is exactly the law of the y before, because exactly of the fact that when you integral with tau is the same thing as if you integral with rho. And this identity of laws says that you have identity of laws for the one-step Euler schemes, which and now you have here a Poisson point measure which is objective, and you can construct this one-step Euler scheme with respect to this objective Poisson point measure, and you construct for the other data, x bar prime, rho bar, you construct exactly the same thing, and with the same Poisson point measure. These two ones, they are defined on the same probability space. This is the space, the step to be done. They are on the same probability space. And now you are doing, you compare the two ones with an L1 calculus. So the distance between theta rho x bar, theta rho bar x bar is less than the distance in L1 of the one-step Euler schemes. There you use some Lipschitz properties of the coefficients, and you upper bound with L1 distances, and appears here is not an F, it's a modulus of T1 minus T2, but T1 minus T2 dW is exactly W1 of rho bar, and you have 1 plus Ct minus S, and you get your estimate. So this is the stability property, and if you have this stability property already here, you see that you have the Lipschitz properties. It's already obtained the Lipschitz property. Up. And so we have the stability, we have the Lipschitz property, and now I have to check the sewing property. So you have YS sewing property. You have YST. So you go from S to T, starting with X. What you have to do is to take the integral from S to T and to cut it as an integral from S to R and to R to T, and so you cut it into integrals. And so one step is to go from X to Z, which is the value of the one-step Euler scheme in R, and then you go to R to T. So you just split the equation into parts. And you notice that Z has the law theta SR of rho. This is important afterwards. And you have to compare this thing with the same equation with Z, but going the Euler, you have to compare with the Euler scheme which starts from Z. So this is you have the same equations, but one time you have to X, one time you have to Z, one time with rho, one time with theta S rho. And in order to compare these two one, you use the stability result which appears before, and you get that the difference of these two ones is less than T minus R, the difference of X minus Z, and this is T minus R minus S. And this is already T minus S squared. So you are done for, maybe the computation is a little, you can do it, it's really elementary. And So you have get that this has the law of theta s t rho. This has the law composition of theta with theta, and this is less than t minus square r minus s. This is t minus s 2. Okay, so you have the same property. Just a remark. I have no times. I have not told here some point. You see, I take here. I say t minus r, r minus s. I have used here the fact that we are in the framework of finite variation, because if I go from t to t plus h, this is of order of h. This was hidden of, maybe this is something that I have not told. Okay. The measures that you have here are measures which integrate z and not z squared. So the process is, these are not compensated measures. These are just Poisson point measures. We are with Poisson point measures which are not very at the level of martingales, but they are at the level of finite variation, h. And here I have used it h times h is h squared, which is already good. If you are in the martingale scale, you have h 1 over 2, and h 1 over 2, h 1 over 2, this h, it doesn't work. So what I am speaking here, it's about finite variation case. In the case of martingale, the situation is a little bit more complicated because you have two scales, the scale of finite variation and the martingale scale. Nowadays, there is a new a guy from London, he has done a stochastic throwing lemma, which seems appropriate in order to work with martingales. And we are working on this nowadays. But anyway, this is not done. Puff. Finally, so up to here I discussed the Euler schema approximation of the construction, the Euler schema approximation of the solutions of these equations. Behind all this, if we want to do numerics, we have to introduce a particle system, because you have to approximate in a way or in another the law of the solution, and this is well done by using particle systems, because you may replace the law of the solution by the empirical law associated with the particle system. So we have the Euler scheme, we have the particle system associated to it, where we replace the law of the solution by the empirical laws. And we prove the convergence, the estimate. We have an estimate of the error. If what we want to estimate is the integral of a test function f with respect to the flow solution. This is what we want to compute. And we prove that this is close to the integral of the f with respect to the empirical measure associated to the particle systems, and the error is equal to C over n. Small n is the step of the Euler scheme. So this is the step of the Euler scheme, and plus C over n 1 over d. Capital N is the number of particles. D is the dimension in which we are working. The proof of this last estimate is using a new result some years ago of Fournier and Guillain, who give such estimates of the empirical measure error. And what I wanted to say is that we may use this kind of, apply this kind of result to the homogeneous Boltzmann equation, but also to inhomogeneous Boltzmann equations. For example, there you have a first component which is the space component, and then the velocities. And for example, if if you have that interacting particles are only the particles which are close each other up to distance r, then the evolution of this equation is of the velocities depends on the evolution of the positions, and the positions do not remain uniform as is the case of the homogeneous equation. And so one may also think to other types of influence of the position in the equations of the velocities. So this is what I wanted to say. Thank you.
When you switch to the particle system, when you you include the empirical measure?
Attends une seconde.
Yes.
Ici? No.
No. After.
Ici?
No, when you have the empirical measure in the system at the end. You say that the results rely on some estimates by.
Ici?
Yes, by Fournier and Guillain.
Pardon?
You say that this relies on some estimates Fournier and Guillain, but I didn't understand if you still use the Sewing lemma in this proof, or it is only...
Non. Ici, on n'emploie plus le Sewing lemma. Ça se fait à la main directement sur le système de particules. Dans cette procédure qu'on fait à la main, à un certain moment, on tombe sur le résultat de Fournier-Guillain qui nous aide à finir avec ça. Mais c'est dans la convergence du système de particules, parce que c'est clair qu'il y aura une estimée de l'erreur du système de particules, n'apparaît plus le Sewing lemma. C'était ça ta question, non?
Okay, let's thank Vlad again.